of your syllabus, and this is the last module of the syllabus. Till date, we have discussed about image enhancement, image segmentation, image restoration, image morphology. When it comes to image segmentation, what we have studied is we have divided the given image into regions, resulting in separate sections. So when we had a discussion on segmentation, we had discussed that any image can be partitioned into sections either by finding the discontinuity or by growing the region. So when it has been done by using the discontinuity, then it is called as edge-based detection. And when it is done with respect to the regions, it is called as region growing, region splitting, and merging. So representing a region involves two choices. That is, I can represent any region using external characteristics, which is also called as boundary characteristics or boundary, or I can represent any region using internal characteristics. That is, the pixels comprising the region. So above scheme is part of the task making data useful to the computer. Next task is to describe the region based on representation. So pictorially I can represent like this. Any image that is segmented will consist of raw pixels or a raw data, that is pixels, which has to be represented, and this representation can be done by external characteristics, or I can do the representation using the internal characteristics. And when I do it using the external characteristics, then those characteristics are called that is can be done using the shape. And when I do it with if represent the information using internal characteristics, that is carried out by using descriptors such as color and texture. For example, in this image, we have alphabet F, which is shown in the first block, and it has been displaced in the second block. It has been rotated in some of the blocks, and its scale has been changed in some of the block. So what is expected whenever it is with respect to description is whenever any character F is given, it should be recognized as F, irrespective of whether it is translated, rotated, or scaled. So this is what is expected when it comes to representation. So even though any image has invariance with respect to translation, scale, rotation, whatever descriptor I define should be translation invariance, scale invariance, and rotation invariance. Now, how can we do this? So, as I discussed previously, which one is to choose when? So, when I want to go for an external representation, and our primary focus will be on shape characteristics. When it comes to internal representation, the is chosen, then primary focus is to represent the regional properties, that is color and the texture. Sometimes we need to have both shape characteristics as well as the color and texture are used when I want to represent both internal and external representation. And whether I go for the shape characteristics or I go for color and texture, what is expected is the descriptors should be insensitive to changes in size, translation, and rotation. So now we'll come to, first we'll discuss about those descriptors which are based on boundary based detection. So boundary as such we know that it is the edge of any region, or it is the closed connected edge of any region. So most of the algorithm require that points in the boundary of a region be ordered in clockwise or anti-clockwise direction. So in this case, we assume that an object and a background, we assume the image to be a binary image with consisting of object and background, wherein object is represented as 1 and background is represented as 0. We also make an assumption that images are padded with borders of zeros to eliminate the possibility of object merging with image border. So, in order to represent a boundary, first methodology which we use is chain codes. So, chain codes are used to represent boundary by a connected sequence of straight line segments of specified length and direction. Typically, this representation is based on 4 or 8 connectivity of segments. The direction of each segment is coded by using a numbering scheme. You can see here this is 4 connectivity of segments and this is 8 connectivity of segment, wherein we have numbered this 4 connectivity as 0, 1, 2, 3 in a counterclockwise direction, whereas in the second image it is an 8 connectivity segment wherein we are numbering from 0 to 7 in a counterclockwise direction, and these are used to represent any image in the form of chain codes. Now, a boundary code formed as a sequence of such directional numbers is referred to as chain code. Digital images are acquired and processed in a grid format with equal spacing in x and y direction. So, chain code can be generated by following a boundary in a clockwise or anti-clockwise direction and assigning a direction to the segments connecting every pair of pixels. So, the problem which we can have in case of chain codes is resulting chain code may tend to be a quite long code. Other thing is, if at all there is any small disturbances along the boundary due to noise or any imperfect imperfect segmentation, that may also cause changes in the code and leading to a wrong chain code. This is how any object is represented in the grid format. So you can see that this is an object which has to be represented using a chain code. So it is enclosed in a grid format. A grid consists of the equal spaces along x and y direction, and these values are mapped to the nearest uh, squares, giving me the sampled image. So we'll now study how exactly a chain code is used for representation of any object. So here I have an object which has the is shown with arrow. The way the object is represented, it is a starting point. Then I have this object has been represented starting from here, goes and complete the and come to the starting point again. So I can represent this object by using a 4 connected segment or 8 connected segment. In this case, there are no arrows in any other direction other than 90-degree, 0, 270 or 180. So either if I go for a 4 connected or 8 connected, both give me the same kind of chain code. So now we'll study how exactly we'll be applying the chain code. So since this is a starting point, I'll just check this arrow. This arrow represents 1 if I go for a 4 connected segment. So this is 1. So this also is 1. This also is 1. And this goes from this end and this is represented as 0. So you can see here 1, 1, 1, then followed by 0. Then we have 1, 0, 1, 0, which is shown over here as 1, 0, 1, 0. After that it is coming down. This is coming down is 3. In the downward direction it is 3. So 3, 0, 3, 3, 3, 0. So we have represented as 3, 0, 3, 3, 3, 0. Then we have 3, 2, 2, 1. Then 2, 3, 2, 2. So we have come to the end point of this object. So this is what is called as chain code. So this chain code has been written taking into consideration 4 connected segments. Now, when I have to write the first circular distance, what we do is we'll be taking the difference between the successive values. So what we do is first value is written by taking the difference between the last element and the first element. That is, here it is 1 and 2. So the difference is 1. After that, what we'll do is 1 on 1. There is no change in the value. 1 on 1. 1 with 1 is the same value. That is, there is no change. 1 is there and again 1. So it is written as 0. Then 1 with 1 is again 0. Then 1 to 0. That is 1. I have to go to 0. So there is 1, 2, 3. Then only I will be able to reach 0. So 1 with 0 is 3. 0 with 1. 0 with 1. I'll go to 1. Reads 1. So 1 with 0, again 3. 0 with 3, that is 3. And 3 with 0, that is 1. 0 with 3 is 3. 3 with 3 will be 0. 3 with 3 is 0. 3 with 0 is 1. And 0 with 3 is 1. 3 with 2 is 3. 2 with 2 is 0. 2 with 1 is 3. 1 with 2 is 1. 2 with 3 is 1. 3 is 2 is 3. And 2 is 2 is 0. So, if at all there is a difference, same value is there, we take two consecutive values, and if the values are same, then 1 is again remaining as 1. There is no movement as such. So in such case only it will be 0. If at all I have first value as 1, second as 0, I need to have one jump, that is 1 to 2. Then in such case the value will be, the difference will be 1. If at all I have 1 followed by 0, I cannot move in a clockwise direction, so I should come by anti-clockwise direction. That is 1 will go to 2, 2 will go to 3, 3 will go to 0. So in such case, you have this value as 3. So this is how the derivative is written, and the first element is the difference between the first and the last component. This is the given object, and this is the starting point. Based on the starting point, and already it is using 8 connected segment to represent this one chain code, 8 connected segment for representing, writing the chain code. So you can see here that we have written the value as per the 8 connectivity. This is 1, 2 upstairs, upwards, then 3, 4, 5, 6, 7, and 0. So if I apply the same thing over here, so 1, 0, 7, 0, and so on. So I'll be writing all the segments, will be numbering all the segments as per the 8 connected segment, and we'll be writing the chain code. As I told you, after writing the chain code, we'll be writing the difference as the difference between the first and the second. How to, I'm at 1, I want to go to 0, and that too in a 8 connect. So I'm over here, then I want to go to 0. So it is 1 to 2, 1, 2, 3, 4, 5, 6, 7. So that's why the value becomes, difference becomes 7. 1 to 0 is 7, 0 to 7 is 7, but 7 to 0 is 1, and so on. So in this way, I'll be writing the chain code, the difference. So once we write the difference, we need to write a shape number. Shape number is always, what we do is, from the first, the difference, we find out what is the minimum value amongst the given in the difference sequence. So I have, in this, I have minimum value as 1, but 1 exists at 2 points here as well as here. But when it comes to writing the shape number, what we do is, we'll check what is what value has occurred after 1. In this case, 1 followed by 7, that is a 6 gems. And when it comes to second one, it is 1 followed by 6 5 gems. So the difference over here is more as compared to the difference over here. So we'll take this one as the first element, 1, 6. Then we'll read this as circular sequence. So 1, 6, 7, 7, 7, 1, 7, 7, 7, 7, 6, 2, 7. In this way, we'll be writing the shape number. So shape number, when it comes to only one minimum value, we can start with that. When there are same minimum value in more than one locations, then I should take that value which has less difference. So, so this is the shape number, and since there are 13 elements over here, so the order of this image representation is 0. So these are some other examples. As I told you, the problem with the chain codes is long chain of codes, and it is easily disturbed by noise. If at all it is disturbed by noise and the pixel is moved from its original location, in such case we'll be having wrong representation of chain codes. Resampling using larger grid spacing is the solution in order to avoid the scale invariance, in order to avoid scale variance. So if I don't want to have any problem with respect to scaling, then what is required is I need to resample the image. How to resample the image? Just put the image on a grid with larger spacing. Then the second problem that arises in case of chain codes is the starting point. Because as I change the starting point, the chain code also changes. Depending on the chain code, the first difference also I need to find out. So since the chain code changes at my change at starting point, it is good to go for better to have a normalization of the chain code. So this normalization is done by taking the first difference which we discussed previously. So always scaling variation is removed by using the grid with the larger spacing, and the uh, starting point, that is with respect to translation invariance, I can remove this by making use of the normalization with respect to by finding the difference. So after that, we'll find out a shape number, that is the smallest integers of first difference circular chain code. This will give me the shape number. We can refer to this example from Gonzalez book. So this is normalized sequence, that is we have a chain code, and what we do is we take the first difference of 4-direction chain code. So first difference of 4-direction chain code is this one. So this is called as normalized circular sequence. So you can see here, we start with 1 or we start with some other point, the chain code will change, but the circular first difference will remain the same. Now, when it comes to rotation, suppose I have an object like this. Now we can see here, this is an object, and if at all it has been rotated. In such case, if at all I have been asked to write the chain code, and I'll be writing chain code for this using this 8 connected segments. So in such case, if at all I start from this point, so I'll go from here and come back to the starting point. So in such case, the chain code will be 0, 0, then 6, 6, 2, 4, 4, 2, 2. That is what is written here, 0, 0, 6, 6, 4, 4, 2, 2. When the same object has been rotated, now my starting point has been rotated and now it has become this point. So I'll start from here. So this is 7, this is also 7, and this is 5. So 7, 7, 5, 5, 3, 3, and 1, 1. Now if you see, this chain code is different and this chain code is different, and I'm getting this chain code mainly because of the difference is mainly because of the rotation of the object. So if at all I want to make it rotation invariant, then Instead of taking the chain code, what we'll do is we'll take the circular first difference. So in this case, the first difference here, it is 0 to 0 is 0, whereas 0 to 6 is 6. 6 to 6 will be 0. 6 to 4 is 6. 4 to 4 is 0. 4 to 2 is 6 and 2 to 2 is 0. Same if I find for the second rotated a circular code of rotated object. 7 to 7 is 0, 7 to 6 is 7 to 5 is 6, 5 to 5 is 0, 5 to 3 is 6, 3 to 3 is 0, 3 to 1 is 6, 1 to 1 is 0. So 1 to 1 is 0. So in this way, I can see that the difference, though the chain codes are different, but their circular first difference remain the same. So if at all, we can conclude that instead of taking the chain code, if we normalize and take the first difference, then the chain code is also invariant. It is rotation. It will give me rotation invariance. No. So the solution to scaling problem is to resample the boundary by selecting a larger grid sample. Then as the boundary is traversed, a boundary point is assigned to each node of the large grid depending upon the proximity of the original boundary to that node. The resampled boundary can now be represented either by 4 or 8 code. The accuracy of resulting code representation depends on the spacing of the sample grids. Now, the chain code of a boundary depends upon the starting point. However, the code can be normalized when we treat the chain code as a circular sequence of direction numbers and redefine starting point so that resulting sequence forms a integer of minimum magnitude. Then we can normalize it. We can even normalize when we can do normalization for rotation by the first difference of the chain code instead of taking the chain code itself. And I have already told you how to write a first difference. So given any chain code, I'll be taking the first difference by taking two consecutive numbers, and the difference will be written as the first difference. Considering the circular first difference, first element is calculated by subtracting the first and the last. So given any chain code, we'll be writing the first difference. First difference is by taking the difference between the two consecutive elements. From that, we'll derive the circular sequence of first element, which is same as the first difference. Only thing is the difference between first and last element is found out and it is placed at the starting. So when it comes to previous slide, this is the first difference, and circular first difference is difference between 3 and 0, that is 3. So which will be written over it. So instead of 3 1 3 3 0 3 0, it will be 3 3 1 3 3 0 3 0. That is what is written in the next slide. These normalization are exact only if the boundaries are invariant to rotation and scale changes. So the problems in the chain code, long code, low noise robustness. So this can be eliminated by resampling, and starting point problem can be eliminated by taking the minimum integer circular first difference. Then angle normalization is done by taking the first difference. Next we'll come to the representation of object using the polygon approximation. So there are many ways of approximating using polygon approximation method, many ways of representing the object using polygon approximation method. So we'll discuss two techniques in this. One is polygon approximation using minimum perimeter polygons. A digital boundary can be approximated with the arbitrary accuracy of a polygon. For a closed boundary, if at all I want to have exact representation of the polygon, then I need to take the number of points to be equal to the number of points representing the boundary. Otherwise, we'll have just an approximation. So if at all I want to go closer to the polygon which I want to represent, then I should take more and more number of points. So minimum perimeter polygon. In this approach, and we are generating an algorithm that compute the minimum perimeter polygon is to enhance a boundary by a set of concatenated cells. Think our boundary as a rubber band. So rubber band always takes the shape of a object. So same concept is used here in case of minimum um, perimeter polygon. So this shrinking produces the shape of the polygon of minimum perimeter. Size of cells determine the accuracy of the polygon approximation here. In the limit, if size of each cell corresponds to a pixel in the boundary, the error in each cell between the boundary and the MPP approximately at most would be root of 2D, where D is the minimum possible pixel distance. This error can be reduced to half by forcing each cell in polygon approximation to be centered on its corresponding pixel in the original boundary. So if you take the object here, and if I want to represent it with the polygon approximation, so we'll have an inside and the outside boundary for this. So if at all I want to approximate using minimum perimeter polygon, then I need to put these points on the object. I should represent it to nearest sampling rate. So the objective is to use largest possible cell size acceptable in a given application, thus producing MPPs with the fewest number of vertices. The circular approach reduces the shape of the object enclosed in a original boundary, the area circumscribed by the gray wall. So now we'll move on to the next representation, that is splitting technique. In splitting technique, the given image is divided into sections. So how to do it? Given any image, let me show you the example. Given any image, if I want to go for a polygon approximation using splitting method, what we do is we'll select 2 points, faraway points on the object. Then we'll connect these 2 points. Then we'll draw the perpendiculars from this line to the boundary of the object. And in that, whichever perpendicular has highest length, that will be kept and rest all will not be considered. So once we have this, and we'll have a value of, we take a threshold value, and if at all this value of this length of the segment is less than the threshold value, in such greater than the threshold value, then again this portion will be divided into sections. Otherwise, this will not be divided into sections. So assuming that after taking the subsection and drawing the perpendicular, if at all, now assuming that this value of this perpendicular is higher than the threshold, then what we'll do is we'll take these 2 points and divide, again join these 2 points, then again draw the perpendicular. And if at all this perpendicular is length of the perpendicular is less than the threshold, then it will not be further divided. Otherwise, the division goes on. In this way, we can approximate the, I can represent the object by polygon approximation using the splitting technique. So we'll move on to the next part. Merging technique, that is no guarantee of corner detection. The problem over here is we cannot guarantee that the corner will be detected. The splitting to subdivide the segment successively into 2 parts until a given criterion is satisfied. So this is polygon approximation. So this is how we are doing in the splitting technique. If at all I have joined 2 points, then from these on we draw perpendiculars using this line and find out which perpendicular has the highest length. Then that will be used for further division. Next, representation of boundary is done by signature. So signature is a method which is used for determining the shape characteristics. So it is a one-dimensional representation of boundary and may be generated in various ways. One of the simplest is to plot the distance from the centroid to the boundary as a function of angle. Let me explain you with the example. So in this example, you can see that I have an object and this is its centroid. So we have a line that joins the centroid to the boundary, and that has been, this line is moved over the entire boundary at a certain angle theta. So one of the simplest way is to plot a distance from the centroid to the boundary as a function of theta. Signatures generated by this method are invariant to translation. There is no problem with respect to translation, but they are dependent on rotation and scaling. Means if at all there is a rotation and scaling happens, then definitely the signatures also vary. Normalization with respect to rotation can be achieved by finding a way to select some starting point to generate the signature. So every time you have to use the same starting point for generating the signature, then definitely we'll overcome the problem with respect to rotation. So it will give me the same signature irrespective of the rotation. So the signatures are nothing but one directional functional representation of the boundary. In order to generate this, plot the distance from the center to the boundary as a function of angles. The signatures are often unique for a region. We can distinguish the region by its signature. It is independent of translation but not rotation and scaling. And these are the signatures for object which is a circular signature